with transfer function. Okay, and we need to get state space from this transfer function. So the opposite. Before we have a state space, we converted to transfer function. Now we need to convert from transfer function to state space. Okay, as you can see here, third order system. Okay, but we cannot measure the behavior of each state. I know it's a third order system because S power 3. So S power 3, that means immediately I will have 3 state variables. So immediately I have 3 state variables. So I will have x1 dot, x2 dot, and x3 dot, which is equal ax plus bu, and so I need to measure each state behavior. That's why we convert this transfer function to state space. So before reaching the state space, we need to convert this S domain to differential equation. So we know the transfer function, it's about cross multiplication, right? So if you multiply C of S times this part, you will get this part equal 24 times R of S. Now, if you get rid of S domain, what will happen? S cubic becomes C double 3 dots. We know C double 3 dots mean D C over dt cubic, and here we have D cubic. Do you agree with me?
Yes,
Yes.
Yeah, that's what happened.
Yes.
Here for S square, I have C double dot. Here I have 26S, it becomes 26 C dot. Every S it's represent as differential. Here I have 24, here only 24 constant times C, because here we have C of S as variable C. Here 24 R of S becomes 24 R. Now let's go further. Select state variables. How to select state variable? We name x1, x2, x3 as a state variable. We know the x dot equal, for state space, x dot equal a x plus b u, and y equal cx plus du. Now we need to select this x. What is this x? Okay, x1, we take it as lowest order, C. x2, we take it as C dot. x3, we take it as x double dot. How? I will show you how. Because if you integrate, okay, each part, it becomes, it give us the original. It will give us the original. For example, here, x or C double 3 dot equal what? If I take this alone, equal what?
D cubic, D.
All these parts go to another side, right? This part will go to another side. So you will have 24R minus 9C dot double dot minus 26C dot minus 24C. Right? Here, when we select, be careful, because we are transferring to canonical form. The canonical form, it has a procedure. It's written here in the beginning. If you go back to the previous procedures, okay, what will happen? He says you have minus A0, minus A1, minus A2, minus A3. So if you identify these parameters inside the matrix, you can know the state space or the state variable. You can name the state variables. We know A0 is related to the first part, x1. Let's go to this canonical form also. Have this canonical form. A sub n, the highest order. A sub n minus 1, lower. A sub n minus 2. Imagine if you have third order system, you are looking for A sub n. What is the A sub n? That means A3, right? And here it becomes A2. If n equal 3. And here it will be A1. Right? So I must have only 3 elements. In our example, I have a question for you here. I have a question. When we make the state space, how many elements it will be here in this row? How many elements, guys?
3.
3 elements, right? 3 elements. So we need to be careful also. We okay, determine the input element. We know the R, it's input, right? R, which is input. And this C, it's as a state variable. So that's why I make C double 3 dot equal this part. So this part I know this as BU. This part will be BU as input. And this part as state variables. I have 3 elements, 1, 2, and 3. These 3 elements will be located in what? It will be located in state space. So these 3 elements, I take it from the lowest order. 24, I put 24 here. I put 26 here, I put 9 here. As you can see here, x1 equals C, x2 equals C dot, x3 equals C double dot. So when we integrate, x1 dot takes x2. x2 dot takes x3. x3 dot takes, because this 3x dot, which is C double triple dot. Just consider C triple dot. And Y as output, okay, it takes x1. Now in form, as I told you before, we take from the least. This 24, take the first, 26, and then 9, multiplied by x1, x2, and x3. Do you have any question?
Inshallah, clear.
Now we have another part, controllability. What does controllability mean? So I limited the converting from transfer function to state space, only one example. Good to know. And here we have controllability, the matrix. How can we define controllability? What does controllability mean? Here in red box, it's a little definitions shows you how controllability is really important. If an input to a system can be found that takes every state variable from desired initial state to a desired final state. The system is said to be controllable, otherwise the system uncontrollable. Why we need to check controllability? Checking controllability, it gives us, okay, a chance to know the system if we can design controller or not. Clear?
Yes.
In two words, to give us a chance if the system can be controlled or not. If the system cannot be controlled, that means no need to, okay, put much effort to design controller for a system. But if the system controllable, yes, we need to do effort to design controller, because sometimes the system is uncontrollable, okay, with full rank, and you can see the states, but the system still uncontrollable. So you cannot determine controllability of the system until you do the test. And we will see together how can we do the test of the controllability. So controllability usually related with the A and B. Controllability related to state matrix A and input matrix, which is B. A with B. So A and B, it will be listed as matrix here. So I create array, okay, I put B first, because B, we know B as a vector. We put the B in the first column, and then we multiply A and B. So when we multiply A and B, and A as a square matrix, B as vector. So when you multiply A times B, you will get vector. How? If this 2 times 2 and this 2 times 1, this 2, it goes with each other, and what's left? 2 times 1. So the result will be 2 times 1, right? This is how you can know the match of
Yes.
multiplication. This internal must match, because how can we define row times vector? This row 2, vector 2. Here row 2, vector 1. Here A square times B. So this A matrix must be square. So you need to multiply this square matrix together and then times B. So as you know, the matrix is not mutual multiplication. So you cannot multiply this A times B and then you go multiply A times B times this result. It gives you wrong. You cannot do this. You need to be in order. So A square, so you need to do this A times A, then times B. And then A square times B does not equal, okay, A, B, AB times like this. Does not equal A times AB. ما تتساوى. So let us take example. Check if the system controllable or not. First, what you need to identify, we need to identify A. This consider A matrix, and this consider as B matrix, as here, as shown here. And this X as state variables and U as an input. What you need to do, you need to memorize this procedure of this state matrix. After you find controllability matrix here, what you need to do, you need to check the rank of the matrix, because this CM is considered as matrix. This CM considered as matrix. This matrix, you need to measure the rank of the matrix. What I mean by the rank of the matrix, how many elements located in each order. This is the rank of the matrix, and we will learn it inshallah together. From there, we can determine if the matrix has a full rank or lower rank. And then we can call the system controllable or not controllable. In this example, A times B, A squared times B. So as you can see here, B, it's located here. This B becomes in the first column. Okay. And then we multiply A times B. If you multiply A times B, this A times B, you will get this column. Let's see it together. If you multiply here -1, 1, 0, you will get 1, this one. Second row, 0 minus 1 times 0 times this vector, you will get -1. Yes. The last row times this vector, 0 times 0, 0 times 1, here -2 times 1, it becomes -2, here -2. Now, make the square matrix, multiply A times A and B, you will get this column. Now, let us check the rank of the matrix. Okay, but checking the rank of the matrix, it cannot become before calculating the determinant of the matrix. We need to check determinant of the matrix. If the determinant of the matrix equals 0, that means the system uncontrollable. If the system or determinant is non-singular, that means the system controllable. What I mean non-singular, so that means determinant does not equal 0. Does not equal 0. From this example, okay, we check the determinant of the matrix as I showed you before, 0, 1, 1 minus 1, 1 minus 2, to find determinant of the matrix, and you multiply this diagonal plus this diagonal plus this diagonal. Let's calculate it together. Now, if you multiply this part, it gives us 0. Plus, if you multiply 1 times 1 minus times 1, and here 1. One plus here -2 times 1 times -2 becomes 4 minus. Now open a new bracket. Now make the inverse multiplications. -2 times -2 times 1, it gives us 2. Here it gives us 0 because 0, 1 minus 2. Here it gives us 4. Right? Now calculate 1 times 1 plus 4, 5. Right? Here 5. Here 2 plus 4, 6. Right? 5 minus 6, -1. It gives us -1 as written here. Clear?
Clear.
Okay, -1. Does -1 equal to 0? No, this -1 does not equal to 0. That means the system determinant here, as you can see this note, determinant is not equal to 0. And the rank is 3 times 3. Y, which is the system non-singular. Why the rank is 3? The rank n, we need to check how many row it has elements. All the row it has elements. Row 1, row 2, and row 3, it has elements. Sometimes we call it rank 2 even in third order system. For example, you have 0, 0, 0. You have 0, 1, 2. 0, 1, 3. What's the rank of this matrix? This rank of this matrix 2. Because the first row filled with 0 is not calculated. Cannot be there. So that's why we call the rank is 2. So imagine you have another system filled with 0. And only one number, which is 3. This I call the rank 1. Why? Because this row 0, this row 0, and this row has at least one element. If the one row it has at least one element, we call the rank 1. Clear the rank of the matrix?
Yes,
You measure
yes,
the rank
yes.
of the matrix from the number of rows. If you have many rows, that means you have 0 rank. Now this is another example to determine the controllability. Determine if the system controllable or not. Third order system, yes, it's more complicated, I know. We have here A matrix and B matrix, and we fill this matrix in controllability in order. Be careful, B, and then AB, and then A squared times B. Here we put B. There is no hard time to find B, only located as is. Second, we multiply A times B. If you multiply this row times this vector, in the first element to give us 0, because minus 1 with 0, 0. 1 times 0, 0. 0 times 1, 0. So here I put 0. Second row times this vector. It gives us 0 as well, because this element related to this element, 0. Minus 1 times 0, 0. 0 times 1, 0. The last row, 0, 0 minus 2 multiplied by 0, 0, 1, it gives us minus 2. Because 0 times 0 plus 0 times 0 plus minus 2, minus 2 times 1, minus 2. And I put minus 2 here. Now let's go to the last part, which is A squared times B. I need to square A first and then times B. And I got 0, 0, 4. What happens if I have matrix 4 times 4? How can you find this determinant matrix? How to find this determinant matrix? You need to put more B, AB, A square B, and then A cubic B. Okay? If it's because this must be match A matrix. How many column you need to add? Because here you have 1, 2, 3. So we need to have 3 elements. 1, 2, 3. If I have 4 matrix, I mean 4 times 4, we need to have 4 elements here. واضح يا شباب؟
يعني كل ما ازيد احط 4
لا تكون match.
5.
Yeah, it must be match. It must match. If أنا عندي 2 second order, يكفيني إني أحط B and AB. لأن I have two column. لأن بالنهاية راح تعطيك matrix. This matrix must match this matrix in size.
تمام تمام.
Now, let me raise and complete the example. The system uncontrollable because determinant equals 0. and the rank of the system is less than the order of the system, which is the rank is 1. This first row 0, second row 0, third row it has a number that we call it 1 rank. And how we determined that determinant is 0? Because we did the same thing. I took the 2 column, and I added here 0, 0, 1 minus 2. If you multiply this part, it gives you 0. If you multiply this part, it gives you 0. If you multiply this part, it gives you 0. Even the back here, 0, 0, 1, 0, 0, 0 minus 2, 0, 0, 0, 4, 0. So the determinant equal 0. In this case, once the determinant equals 0, it's immediately you say the system uncontrollable. So in this example, we don't have to consume much time to build a controller because the system itself uncontrollable. The system itself uncontrollable. Yes, there is another technique to make the system controllable by adding some states variable. Okay, but this is not in your level. In your course, you are committed only to identify the system controllable or not controllable. Okay. So this example shows us the system uncontrollable, completely uncontrollable, with less rank. With less rank. A rank is 1. Okay. Let's take a break now and to go back to the observability.
Okay.
Yalla, we are back. Observability part. So the observability part, it's related with state matrix and with the output, with A and C, with A and C. So observability is completely observable of the matrix in this form, as you can see here, but still this O, it must match the size of A. If this A 3 times 3, this must be 3 times 3. Because we need to select here, as you can see here, C, or C times A, C times A square, C times A cubic, and C times A. And you see how many row here you have in state matrix. You need to match it with, you need to match the order of A matrix with O matrix here. And it's still, to determine the observability is similar to controllability. We check the rank and we check the determinant of the matrix. If the determinant does not equal 0, so the system observable. So what's the observable? What's the observer? Maybe this is the first time to hear about the observer. So observer, it's another plant. So we have here a plant, original plant, as you can see here. Original plant, to measure the output or to estimate the output, you need to build another plant. We call it observer. We call it observer. So from this observer, we have a controller, feedback controller. So we make sure when we measure the outputs of the system, I will have two responses. I will have two responses. One for Y and one for Y hat. Y, which is the original output, plant output Y, and Y hat, which is estimated out. This usually measured, okay, to compare and to estimate Y hat if you cannot measure the state inside. So sometimes Y only shows you 1x. Okay, so you need to measure the output. You can measure 1x by this form. So still we have open loop and closed loop in this form, as you can see. In the left side we have open loop observer. In the right side we have closed loop observer. Closed loop observer. So this is only in state feedback design using observer to estimate unavailable state variables. To estimate unavailable state variables. We have two. We have here in this form as open loop, and here we have as a closed loop. Closed loop why? Because the output of actual plant, okay, it's feedback into observer. It's feedback into observer. So what's the observer for? Inshallah, we discuss it next in part 2 of the state space. So here example to determine the observability. As we mentioned before, only we relate A matrix with C matrix. Okay, and we know here this matrix is about 3 times 3. We have 3 rows and we have 3 columns. So we make sure here we have 3 rows. So first we start with C and then C times A and then C times A squared. So as you can see here, C multiplied by A squared. So you need to find A squared value. And then you multiply C times A. As you can see here, for C part, this is the C. 0, 5, 1. I put it here 0, 5, 1. As is. This is your C. So now multiply C times A. Let us multiply C times A. It's a matrix commutation. 0 times 0, 0, 5 times 0, 0, 1 times minus 4, minus 4. So this is the first element, minus 4. Again, we multiply C times the second column. 0 times 1, 0. 5 times 0, 0. 1 times minus 3, minus 3. So minus 3 will be here. Third column. 0 times 0, 0. 5 times 1, 5. Right? 1 times minus 2, minus 2. 5 minus 2, 3. So 3. The last part, you need to multiply C times A squared. Please find A squared. Multiply 3 by 3. Multiply this matrix together. Once you find A times A, go and multiply C times A squared. You will get this part. Now, check the rank. It seems the matrix has full rank. This rank full, this rank full, this rank full. So the rank of 3, yes. And how about the determinant? Determinant, it can be found by 0, 5, minus 4, minus 3, minus 12, minus 13. You multiply these together with different color. This line plus this line plus this line. All these here plus, and you have major negative here. It must put negative. Why negative? Because we need to subtract another element, which is 1 minus 3 minus 12, and then 0 times 3 times minus 13, and then 5 times minus 4 minus 9. You put it here. And then you find determinant. Determinant, we got minus 344, which does not equal to 0. Okay. So once we find that determinant not equal to 0, we can say the system observable. The system observable. So this system is observable because the determinant does not equal to 0. Clear?
Mina.
Yes, yes.
I need to hear from more than one.
Clear.
Yes, Doctor. Yes.
Okay. Now we have this example, which is second order example. We need to check the observability of this matrix. We take A, we take C. So only we committed to, we know that this matrix, it's about 2 times 2. So it's enough to find C and CA. Because this shows 2 rows, right?
Yes.
Yeah, this row, first row, this is second row because it's second order system. So here you can see this is 5, 4 as the first row, and second row C times A. We multiply 5 times 0, 0, 4 times minus 20, minus 5, which is minus 20. Now multiply 5 times 1, 5. 5 multiplies by 21 over 4, which is minus 21. Which is minus, no, 5 times 1, 5. 5 and then 4 times 21 over 4. It gives us minus 21, which is minus 16 here. Now you can see this matrix has full rank. The rank now is full, right? All the row it has it. Okay. So find determinant. Determinant will be 0 because determinant in second order system easy to can be calculated. Multiply this diagonal minus this diagonal. So if you multiply 5 times 16 minus 16 minus 20 times 4, what you will get? Here minus 80, right?
Yes, minus 8.
Okay. How about this? 5 times minus 16? 16, 32.
minus
30,
80.
minus 80, right? So minus and minus becomes positive, and then becomes 0. So your determinant is 0. So once you have determinant 0, what we call it? We call the system unobservable. The system unobservable, completely unobservable. Why? Because determinant equals 0. Determinant equals 0. So we don't have to worry about the observer. We don't have to design an observer because the system unobservable. Even you have this output, it has 2 elements. So this output can shows you x1 and x2, but you cannot measure it. You cannot measure these x1 and x2 because the system unobservable. Because this y shows you 5 and 4. Okay, multiply by x1 and x2. x1 and x2, it's available in the input, but you cannot measure it because this measurement involves us to design an observer, and this observer, okay, this observer needs to be checked if the system itself is observable or not. And we found out the system is unobservable, so no need to design an observer and controller to observe the output from the actual plant. So that's why we call the system unobservable. The system unobservable. Do you have any question?
ليه مش عارف.
Inshallah. Okay.